Welcome to our new unit on radical equations. We are going to begin with learning how to simplify radical expressions. So here's a property you need to remember for multiplication of radicals. If you have a and b underneath an nth root, then you can separate whatever's on the inside of that radical, so that will become the nth root of a multiplied by the nth root of b. So for example, the root of 21 is the same thing as saying the root of 7 times the root of 3. So now also recall what a mixed radical is. A mixed radical will have a number in the front and also a radical beside it. That is a mixed radical, and you can write it as an entire radical that's completely enclosed underneath the root sign. So in order to get the entire radical back from to root 4, if I want to put this back in here, we probably want to think backwards. How would I get root of something equals to 2? Well, we can get that if we had a root of 4. So if I change 2 to root 4, this would be the same thing. So we know the root of 4 is equal to 2. And if I want to multiply using the rule I just stated, this is going to be the root of 16. And that would be your entire radical. That's the same thing as saying 2 root 4. Let's look at arranging in order from greatest to least. So to do this, we're going to convert all our mixed radicals into entire radicals and then order them from there. So for this first one, we have 5 root 2. 5 I can change to root of 25 because the root of 25 is 5. And then we still have that root 2 here. 25 minus 2 is the root of 50. Again, I am using the rule we just stated about multiplication properties of radicals. Okay, now we're going to move on to the next one here. We have 2 root 5. 2 can be expressed as root 4 times then root 5. Which is root of 20. And then this last one here, we have 4 root 3. Instead of 4, I can rewrite this as root of 16, because the root of 16 is 4. And then 16 times 3 is 48. Now I can order this from greatest to least. So we have the root of 50, the root of 48, and the root of 20. If we were to reorder this from greatest to least, or we can write it as the original mixed radical, so that would be 5 root 2, 4 root 3, and 2 root 5. Moving on to b, same sort of thing, but if you notice what the radical is, we have the cube root of 2 consistently. So that means that could be our frame of reference as like an x. So comparing 9x, 11x, and 8x, that's pretty easy to reorder. We're just going to reorder by the coefficient or the number in the front from greatest to least. So that'd be 11 cube root of 2, 9 cube root of 2, and then 8 cube root of 2. And if the radicals have different indices, you could also use the calculator to find the approximate value of each and then reorder. For the most part, we're not going to use much calculator in this unit, but there are going to be some times, and it will be indicating the question or section of when you're going to use your calculator in this unit. So here it does say use a calculator, so we're going to go ahead and put this into the calculator. Remember that not all of them are going to be square root or cube root, so you're going to have to look for the nth root option in your calculator when you're doing this. So 3 times the 4th root of 8 is about 5.045. When you put that in the calculator, 4 root 2 is about 5.66, and lastly, 3 cube root of 5 is about 5.13. So now we're going to order this from greatest to least. Our greatest one is going to be 4 root 2. Then our next one is 3 cube root of 5. And then our smallest is 3/4 root of 8. For the division property of radicals is fairly similar. So if you have the nth root of a over b, you can separate it so it's nth root of a over nth root of b. So for example, let's just say that we have the square root of 9 over 4. You can rewrite this as the root of 9 over the root of 4. So to simplify radicals, we should always look at the index. The index is the nth part of that root. So n equals 2, then you want to look for perfect squares. If n equals 3, you want to look for perfect cubes, and so on. So we're going to rewrite the cube root of negative 16 over 135 as a mixed radical. So because we have an index of 3, I have to look for perfect cubes. Perfect cubes would be something like 2 cubed is 8, so 8 is a perfect cube. 3 cubed is 27, so that is a perfect cube, and so on. So looking at what we have underneath our cube root here, we have a 16 in the numerator. I'm going to try to rewrite 16 as a product using perfect cubes. So I can rewrite 16 as 8 times 2, because that is also 16. The 8 is a perfect cube, so that means I could eventually take this out of our cube root later. For the next one, we have 135 in the denominator. Because it ends in a 5, I'm probably going to multiply 5 with something. And it happens to be 27 times 5 is 135. And 27 is a perfect cube, so this is going to work out. Now I'm going to do my simplification. I'm going to separate this 8 over 27 with the 2 over 5. Just because I'm able to simplify the 8 over 27. The cube root of 8 is 2. The cube root of negative 1, which is where we have that negative in the front, is just negative 1. Then the cube root of 27 is 3. And then we're left with the cube root of 2 over 5. And we'll just leave it just like that. Okay, for the next question, we want to write this as an entire radical. Our nth root is 4, which is our index. I'm going to leave the negative on the outside because our index is even. So if I try to put this back in, the negative will disappear, and we do need this negative. So I'll just leave it on the outside, and this 3 is what I'm going to try to put inside the radical. So I have to reverse what happened to it. Think about this. If we had 3 to the power of 4, and we take the 4th root of it, the 4th root and the power of 4 are going to cancel out, and you're just going to be left with 3's, and that's exactly what we have here. So, to put it back inside the radical, it'd be 3 to the power of 4. And we still have 2 over 27 here. Then my next step, to continue to simplify this, I'm going to rewrite 27 as 3 to the power of 3, just so I don't have to use a calculator to simplify this. 3 to the power of 4 divided by 3 to the power of 3, I'm just going to subtract our exponents, which would be 1, 3 to the power of 1. Then lastly, 3 times 2 is 6, so our final answer is negative 4th root of 6. Moving on to example 4. For which values of the variable is each radical defined? Simplify the radical if possible. So I'm going to try to simplify the radical, and then we can determine the values of the variable which the radical is defined. Remember that anything inside a square root or a fourth root, it has to be positive. So just by looking at this, because we have a squared here, a can be anything. Just by looking at this. Because even if a was negative and I square that, we're going to get a positive number anyway. Now let's try to simplify this a bit. Because we have a square root, I'm looking for perfect squares. So I want to rewrite 45 as maybe 9 times 5. Because 9 is a perfect square. And I can take the square root of 9. I'm just separating them so that we can take the square root of them individually. So the square root of 9 is 3. We also can take the square root of a squared. There's an invisible 2 here because it's a square root, so this is going to cancel with the exponent of 2, and we're just going to be left with a. And then root 5 is nothing we can change, so we just leave it as that. Moving on to part B, we know that z has to be positive because we have a even root. And if we take a look to see how we can simplify this, there's actually no way for us to simplify this because the number 7 can't be taken to the fourth root. And I can't rewrite this as a product of anything that I can take the fourth root of, so we just leave that as is. Then lastly, for C, we have the cube root of 24y to the power of 5. I'm going to try to rewrite 24 using a product of perfect cubes. So 8 times 3 can give us 24, and 8 is a perfect cube. Then for y to the power of 5, I'm going to rewrite this into y to the power of 3 multiplied by y to the power of 2. Why? Is because I can take the cube root of y to the power of 3 very easily. I just did that by rewriting this y to the power of 5 using our exponent laws, where we can just add our exponents when we are multiplying with the same base. Okay, so I am going to try to simplify anything that we could take the cube root of. So this one here I could take the cube root of. I can take the cube root of this as well. So the cube root of 8 is 2. The cube root of y cubed is just y. And then we're left with 3y squared. And there's nothing we can do about that, so I'm just going to leave that as is. And because we are cube rooting, y can be positive or negative. So y can be